Hi there, in this video we're going to start talking about some of the calculus concepts that we'll need, that will be our foundation to go on to the next big concepts. So we're going to work towards velocity, average, and instantaneous, and the idea of a limit after this section. So our first example, suppose you travel 40 miles in a half hour. What is your average velocity? And so average velocity, what is it? Well, velocity is distance traveled divided by the time that it took to travel, right? So we're going to say this is distance traveled divided by time taken to travel. So in this case, we have, what was the distance traveled? Well, we've traveled 40 miles, and we did that in half an hour. So that means that this is going to be 80 miles per hour. And so does that mean you were going 80 miles per hour the entire time? No, right? So this is the average velocity. So you could have been going 60 at times, 40, right? 0 if you were stopped, and then possibly higher than 80 at some point in order for the average to be 80 miles per hour. So hopefully you were somewhere that the speed limit was okay to be going 80 miles per hour. So anyway, but here the concept is average velocity. So distance traveled divided by the time taken to travel that distance. So let's look at an example. So we have a rocket launched vertically upward from the ground with a speed of 96 feet per second. And if you ignore air resistance, you'll do that in Calc 3. A formula that gives us the position after t seconds is this for this particular rock, minus 16t squared plus 96t. The position is measured in feet with 0 corresponding to the ground. So let's find the average velocity of the rock over the following 4 intervals. All right, so let's start with on 1, 2. We know from above that the average velocity is distance traveled divided by the time taken to travel. So what does that mean when we have a position function? So that means essentially we have the change, the distance traveled is going to be the change in position, and then divided by the change in time. And think about with that first example about you driving 40 miles, right? The distance traveled is from your initial position. So if you were at home or at school, and that's your initial, and then you travel 40 miles, that will be your ending time, your ending position. So then the distance traveled is that change in position. And then the time taken to travel is the change in time. So the change in position is given by, well, this is our position function. So what's going to be the change in position between 1 and 2 seconds? So that means that the change in position is going to be s of 2 minus s of 1 divided by 2 minus 1. And so let's figure out what that is. And so why is this? So let's look at the graph of that function of our minus 16t squared plus 96t. So this is going to be a parabola that opens downward, right? Because of the negative there, that's going to make the parabola open downward. So let's see what that looks like. So what we're looking at over here is this function. And so notice that it has intercepts at 0 and at 6. And you can quickly see that from the function that we have s of t equals minus 16t squared plus 96t. If you factor out the minus 16, you're left with, or minus 16t, because they both have a t, you're left with t minus 6. And so you can see that the x-intercepts or t-intercepts are going to be 0 and 6. But we're looking at the average velocity between on the interval 1 and 2. So we're looking over here. Here's 1 and here's 2. So we are looking at that change, right? So the average velocity will be then the change in position, which will be this, divided by the change in time. So how do we find the change in position? You have to do s of 2 minus s of 1. So that's why I'm doing that up here, s of 2 minus s of 1. So let's figure out what that is. So s of 2 minus s of 1 divided by 2 minus 1. In our case, with this particular function, I'm going to make use of brackets here. So it will be plugging everywhere you see a t, we're going to plug in 2. So this is going to be minus 16 times 2 squared plus 96 times 2. And then we'll do the same thing with 1. So minus 16 times 2 squared plus 96 times 2. So this is s of 2 minus, and then same thing with 1. I'll make a note here. So this is s of 2. So replace the t's with 2's. And this is s of 1. And then the whole thing divided by the change in t, 2 minus 1, which is 1. And so let's compute that out. So when you put this in your calculator, or you can do it in your head, maybe. So we'll get 128 there, minus 80 for s of 1, divided by 1. So I just get 48. And what were our units? Let's see, the position is given in feet. The position is measured in feet. And how do I know that it's seconds? Notice the speed here is at 96 feet per second. So then I know that the time is being measured in seconds. So then this is going to be my change in position is feet, and the change in time is seconds. So this is going to be feet per second. So the average velocity on the interval 1, 2 is 48 feet per second. So for that interval. So now let's try to find what about between 1 and 1.1. And what we're working towards here is towards part B. Based on the results of part A, estimate the instantaneous velocity at x equals 1. So my goal is to talk about the difference between average velocity and instantaneous velocity. So let's look at on the interval 1 to 1.1. So we'll do the same thing that we did for between 1 and 2. So the average velocity then is going to be, in this case, s of 1.1, the one that comes after, minus s of 1. Now the nice thing about this problem is that, notice that we keep using s of 1. So we already know that that's 80. And so I just really need to find s of 1.1. So what is s of 1.1? So it's going to be minus 16 1.1 squared plus 96 times 1.1, and then minus s of 1, but I already know that that's 80 from previous work. Divided by the change in time, 1.1 minus 1. So let's do the math on that. So what do we get? So when you plug in 1.1 on your calculator, I don't think we can do that one in our head. So we're going to get 86.24 and then minus 80 all over 0.1, which gives us 86 minus 80 is 6, so 6.24 divided by 0.1. And this one we don't need a calculator, just move the decimal place over, so 62.4, and our units are still feet per second. And we just continue to do this. So notice what's happening. So we went from, on the interval 1, 2 is 48 feet per second. Now 1 to 1.1. Notice 1.1 is a lot closer to 1 than 2 is to 1. So now we went to 62.4 feet per second. And so let's try part 3, what about between 1 and 1.001? What's going to happen there? And our goal is to then try to make an estimate for what's happening right at 1. And so let's do our average velocity again here. So it's the change in position. So S of 1.001 minus S of 1 all over 1.001 minus 1. And so same thing, right? Let's put that into the function. So minus 16t squared, so 1.001 squared plus 96t, 1.001, and then minus S of 1, which we already know that's 80, all over 0.001. So again, let's put that on our calculator and see what we get. So after we put this on our calculators, we get for S of 1.001, 80.0639, and then minus 80 over 0.001. So when we do that computation, you should get 63.98 feet per second. Don't forget your units. So do we have a guess for the instantaneous velocity at 1? So let's summarize what we have. So on the interval 1, 2, what was our average velocity? And then same thing for the interval 1 to 1.1, what's the average velocity? And then 1 to 1.001, what was our average velocity? So for on 1, 2, our average velocity was 48 feet per second. On 1.1, our average velocity was 62.4 feet per second. And the last one we just did, 63.98 feet per second. Do you have enough information to make a guess for the velocity at t equals 1? I'm tempted to say 64, but so let's try, how about we try one more real quick. So on your own, try, what about if I add an extra, let's do an extra 2 zeros. So 0, 0, 0, 0, 1. So just change everything in your calculator to add 2 extra zeros and then see what we get. So I'll give you a few seconds to do that on your own. Pause the video and then come back and see what the answer is. Okay, so now that you have worked on it and unpaused your video, what did we get? Yeah, 63.99 feet per second. So now my guess of 64 is starting to feel a little more comfortable, right? So I could probably guess that the instantaneous velocity at t equals 1 is around 64 feet per second for instantaneous. What does it mean to be instantaneous velocity? Right, so back on that first problem when I asked you about your average velocity if you drove 40 miles in half hour, one of the things I said is you weren't always going 80 miles per hour, right? You were going, your speed changed. So if I wanted to take a snapshot, so think about if there's an officer giving tickets on the highway, and then right when they clock you at your speed that you're going, that is instantaneous velocity, right? A police officer is not going to follow you to see if you violate the speed limit and take your average velocity and give you a ticket based on that. Now they have the radar guns that clock you at a specific point in time at a certain speed. So that is your instantaneous velocity. What is the velocity at that snapshot in time? And so that's kind of what we're doing here. We have all these intervals, but we're trying to see what happens right at 1. And so going back to this graph, notice that if I connect the dots between these 2 points, pretend that those are connected. So this is what we call a secant line. And so that was between 1 and 2, right? What happens then we moved it to 1.1. So if, this is not to scale. So pretend that that's 1.1. So then this is going to come somewhere over here. And now I'm going to have another secant line. So this will be my secant line on 1 and 1.1 versus my secant line on 1, 2. And so the idea is what happens when we get right on 1. So if I'm able to draw a line just at that it touches 1, now this is only touching at 1 point. Instead of 2 points. Right, notice that the blue line is touching 2 points. The green is touching 2 points. Now this one, I know my graph is not the best, this is touching only 1 point. So this is what we call a tangent line. And the tangent line is what gives us the slope of the tangent line is what gives us the instantaneous velocity. And the slope of a secant line is giving us average velocity. So here we can say, well, we think that the instantaneous velocity is going to be 64. Now we haven't done the last part, which is on the interval 1 and h. So before we do this one, let me write the general average velocity for given a position function. So in general, for any function, any position function, say s equals f of t, where this is the position function, the average velocity then is equal on AB. Average velocity on the interval AB is equal to f of b minus f of a over b minus a, right? So the change in position over the change in time. So for our function, our position function is f of t equals minus 16t squared plus 96t. And we want to find the average velocity on the interval 1 and 1 plus h. So that means that this is going to be f of b, right? So looking at this, this is like our a, and this is like our b. So it'll be f of b, so f of 1 plus h, minus f of a, so f of 1, all over b, so 1 plus h, minus a, minus 1. So this just becomes h, so f of 1 plus h minus f of 1. So this might look familiar already. In prior sections, we did the difference quotient, and that's what it looks like. So notice the difference quotient really comes from finding the average velocity on an interval for a position function. All right, so what is f of 1 plus h? So f of 1 plus h, let's plug it into the function. So it'll be minus 16, 1 plus h squared, plus 96, 1 plus h, right? So you replace every t that you see in the function with 1 plus h. All right, and let's simplify that. So f of 1 plus h is negative 16. Multiply this out. 1 plus h quantity square means 1 plus h times 1 plus h. Make sure you FOIL this properly. Don't make the mistake of saying 1 squared plus h squared. Don't forget about the middle term. 1 plus 2h plus h squared. And then distribute the 96. So plus 96 plus 96h. And let's distribute this. Minus 16 into there. So we're going to have minus 16 minus 32h minus 16h squared. and then plus 96 plus 96h. And do we have any like terms? Yes, we have the minus 32h, the 96h, and we also have the constant terms 16 and 96. So we're going to get, what do we get? Let me write it in descending order. So I'll have negative 16h squared, and then 96h minus 32h. Well, that's plus 64h, and then minus 16 plus 96 gives us plus 80. So that's f of just 1 plus h. And now f of 1, we already know from our work in the prior examples that f of 1 is 80. So we already know f of 1 is 80. So putting it all together for our average velocity on the interval 1, 1 plus h, right? This is f of 1 plus h minus f of 1 all over h. So putting it together, we're going to have f of 1 plus h, this part, which is what we found here, right? F of 1 plus h. So this is going to be my minus 16h squared plus 64h plus 80, and then minus f of 1. So f of 1 is 80, so we're going to put that in here. So minus 80 all over h. And so notice that our 80s, as we combine like terms, our 80s here give us 0, positive 80 minus 80 is 0, and we're left over with things that have an h. So this should look familiar from the process of simplifying the difference quotient, right? Everything that's left in the numerator usually has an h, and then we can factor out that h. So I can take out an h and say minus 16h plus 64. Remember, the goal with simplifying the difference quotient is that we get rid of the h on the bottom. And now, because I have multiplication here, I can get rid of that. So h divided by h gives us 1. And so our final difference quotient answer will be just minus 16h plus 64. And so this becomes the average velocity on 1 plus h. And that's it. So notice that if you ignore the h part, the 64, this is what our guess was for the instantaneous velocity. And that is because notice that the h, so when we look at the intervals, we were going from 1 to 2, 1 to 1.1, 1 to 1.001, 1 to 1.000001. And so that distance between 1 and on the interval keeps getting smaller and smaller and smaller until we are approaching just 1. So if that distance gets really, really small, close to 0, so that's what the h is, right? That distance on the interval. So if that h is really, really, really close to 0, then when h is really close to 0, this minus 16 will be, we can essentially ignore it, because if h is, it's almost like plugging in 0 for h. So this will go away, and you'll be left with the instantaneous velocity right at x equals 1, or t equals 1, which will be then 64 feet per second. And so that's how we can use the difference quotient in average velocity to approximate an instantaneous velocity by doing on the a plus h interval and letting h be really close to 0. All right, on the next video, we'll do an example of another problem. And I actually want you to try this problem on your own, and then on the next video, I'll give you the answer. So try this example on your own. Pause this video so you can read the whole thing, and then go to the next video to see what the answers are.